I want to discuss carbon-13 NMR, and I want to start our conversation by comparing it to a technique that you may be more familiar with, which is hydrogen NMR. And there are a couple of things that I want to mention in this comparison. I want to start off by pointing out that carbon-13 NMR signals are weaker than hydrogen NMR signals, and this is due to a couple of reasons. The most important factor is that only about 1% of the carbon in a sample that you might be analyzing is carbon-13. Most of the rest is carbon-12. This means that even if the signal strengths for a carbon atom and a hydrogen atom were the same, which they're not, only 1% of your carbon atoms are even giving you a signal at all. And this results in a weaker signal requiring more sample and longer collection times. Related to this is the fact that we don't see coupling between adjacent carbon atoms like we do see between nearby hydrogen atoms in the hydrogen NMR. And the reason for this is because only 1% of the sample is carbon-13, you're unlikely to have two adjacent carbon-13 atoms that can couple with one another. Another difference is that there's no integration information available. Because of the way that the carbon-13 NMR spectrum is collected, and I don't want to get into the details of that right now, we cannot look at the area underneath the peaks and say that there are two of this type of carbon and one of that type of carbon and so on, similar to the way we do with a hydrogen NMR spectrum. Another difference between the two is that there's a larger chemical shift range for carbon-13. In the hydrogen NMR, we're typically looking between about 0 and at most 12 ppm for the stuff that we'll be doing this semester. In the carbon-13 NMR, we're generally looking at a much larger range, usually between about 0 to 210 or so ppm. Despite all of these differences, though, the same general trends are observed in the C-13 NMR as in the hydrogen NMR. In other words, more electronegative groups tend to shift your signals further downfield. Aromatic groups in double bonds, alkenes, tend to be further downfield, though in C-13 NMR they're closer to one another than they are in hydrogen NMR. And a methyl is further upfield than a CH2, which is further upfield than a methine. And I want to look at some examples of this, and I want to start by looking at a chart that shows the general range of chemical shifts for a lot of the things that we'll be talking about. If we look at this chart, and this is in ppm, even though it isn't labeled on the axis, we see that the furthest upfield signals are the ones that have no electron withdrawing substituents on them, such as the methyl, the CH2 a little bit further downfield, and the CH a little bit further downfield than that. If we put an electronegative atom like an oxygen on our carbon, the carbon attached directly to the oxygen shows up further downfield. Further still downfield are our alkenes and our aromatic rings. And finally, we have our carbonyl groups, which are on the high end of our chemical shift range. Depending on what's attached to the carbonyl carbon, it's either a little bit further downfield or a little bit less far downfield. I want to look at a couple of examples of C-13 NMR spectra, and I want to start with this one. And some of the things that this spectra tells us about the molecule it's from are, first, that there are 6 types of carbon in the sample. And we can number these 1, 2, 3, 4, 5, and 6. But you might also notice that signal 6 is a little bit further downfield, so it probably has an electronegative atom on it. If we looked at our correlation chart that we just looked at, that's in the range of a carbon-oxygen bond, and this is actually the C-13 NMR spectrum of hexanol, one hexanol. And we can number these signals 1, 2, 3, 4, 5, and 6. I want to remind you that the C-13 doesn't tell us the number of carbons in the sample, but the number of types of carbon in the sample, because we can have symmetry in a molecule. And this spectrum is an example of that. We've got 4 carbon types here, but that does not mean we have 4 carbons. This, in fact, is the C-13 NMR spectrum for 4-heptanol, which has 7 carbons in it, but because of the symmetry, we only have 4 different types of carbon in the molecule.